Part B, efficient polynomial evaluation. Yeah. All right. Part B.1, the first topic, evaluate the polynomials. You know how to evaluate polynomials. Everyone here knows how to evaluate a polynomial. Yeah. Here the question. Now we really get to the key part of our algorithms class. When you can do something, you want to do it in the best way, right? Yeah. Everyone can evaluate, but do you know what is the best way to evaluate a polynomial? That's different. Best way and just the one way, that's different. Yeah. You will see how big is the difference. You will see it. How big is the difference? Huge. Yeah. Here, let me just present the whole story, how big it is, the difference. Yeah. All right. First, let's look at the problem description first. Yeah. Given a polynomial, the standard form like this. Okay? Yeah. It's a general polynomial. Here you can see the degree is n. Yeah. Coefficients a0, a1 through an, all given. Yeah. You just assume the constant coefficients all given. Yeah. And the variable is x. Yeah. X unknown, the variable. Then at the runtime, the user provides you the value of x, that variable. The question is, you need to find the value of the polynomial. You plug in x into that p of x formula, then you calculate. You find the value of px. Yeah. But the question is, the question, how to evaluate p of x efficiently? The fastest as you can. We want the fastest way. Response time is very important here. It's not your answer is correct or not. We know it. It's important. You have to give a correct answer. But that's not enough. We want the response time very fast. That's the main concern, response time. Yeah. All right. So let's do some analysis. Yeah. Right here. Yeah. All right. So here, at the first view, this problem is so simple, right? Yeah, plug in. Everybody knows how to plug in a number. Why we need an algorithm, right? Yeah, yeah. Plug in. Yeah, and it looks like the method is pretty good, right? Yeah, plug in, get a value. Most of you already very satisfied with that answer, right? Yeah. Nobody complain. When you plug in a number, will you complain? You know, I'm not happy with this answer. Yeah. Yeah. So here, now we want to really do analysis. Yeah. The reason that nobody complains because people do not feel it's a bad one. It's a bad solution. The reason people do not complain, they feel it's acceptable. Yeah. All right. But for us, we are computer science students. We study algorithms. We want to solve real-world computing problems in the best way. In the best way. Yeah. So here, we want to dig into it. First, we want to see how fast it is. First, we want to know how fast this method is. Then the second question, can we improve it? Can we do better than that? Yeah. So that's the typical consideration for algorithms. Yeah. All right. Here, the next important question, basic fundamental question of this class. How to measure efficiency. Here we are talking about efficiency, right? Yeah. But do you have a measure for it? Do you have a special measure? Do you use a number to tell people it's efficient or not? Efficiency. So we need a measure, right? Yeah. So the basic question. Yeah. The first measure we can imagine execution time. Execution time. Yeah. Because we can clock it. We see, how many time units we need to complete. Yeah. That's the straightforward measure, right? Straightforward measure, yeah. All right. But that measure usually not stable. Not stable. Yeah, so that's why usually it's a not good measure. Execution time, usually it's not a good measure. Why not stable? Because we don't know which machine we run that program. Yeah. We may run that algorithm on different computer machines. The hardware is different. Some hardware is supercomputer, right? Some hardware, just the laptop, right? Some hardware mobile device. Is it possible that we punch the key, mobile device? So we have some calculator, right? We can do the calculation. Yeah. So based on different computing devices, the execution time could be different. That's why we say not stable. Yeah. So we're not satisfied with execution time measure because not stable. Yeah. So we want to find a stable measure. Here, this is the different stable measure. We using number of additions and a number of multiplications, using concrete numbers to measure the efficiency. Then it will be more stable, right? Yeah. Number of additions, number of multiplications. When you run the algorithm on supercomputer, old laptop, you use the same number of additions, right? You use the same number of multiplications. So then, stable. It does not rely on your hardware devices. Okay? So it's a better one. So in this class, we like to use a stable measure, efficiency measure. All right. Okay. Next, our first try. So here, we want to do analysis. Yeah, here, let me just use a stick to point. Points something. Now here, we want to do analysis. Okay. All right. First try, straightforward algorithm. So plug in, that's the straightforward. Yeah, plug in. Do additions, multiplications, that's the straightforward algorithm. We want to count how many additions, how many multiplications here. Yeah. All right. So, all right. First, let's look at multiplications for each term. Yeah, there are many terms, right? Certain number of terms. The first term, we don't need a multiplication, right? But starting from the second term, each one, we need to do certain number of multiplications. Now, we want to count that number. We want to accumulate the total number of multiplications for plug-in method. Plug-in method, okay? Yeah, straightforward, plug-in method. So for a typical term, a sub k times x to the kth power. That's a typical term. Can you see how many multiplications do we need to calculate this just the one term? Can anyone see it? How many multiplications do we need? Okay? Easy?
I think it's k.
Good. It's k. K. All k plus 1. You say k plus 1. You say k. One must be correct. The other must be wrong, right? So here we need to tell which one correct, which one is wrong. We have two answers. Or at least look reasonable, right? But how do you tell one is correct, the other is wrong? Strategy. We're learning strategy. You can apply it. Strategy.
Would it be k because if you include the coefficients, it would be a total of like k plus 1 terms multiplied together. So that means it's a total of k multiplications. So if like you have 7 numbers and you multiply them, that would mean you're multiplying 6 times.
Yeah, good. Yeah. You give me, he said k. He said k. Yeah, because 7, x to the 7th, you need 6 multiplications, right? Yeah, what he said, then another multiplication coefficient. He explained it should be k. Yeah, convince, explain your answer. Yeah, correct. Yeah, k is correct. Yeah, but here, so here I give you the reference in the textbook. All right, here, in this situation, here I just tell you, this is a typical situation in the real world, right? Yeah. When you encounter this situation, use the strategy we just learned. So what's that? Try the simplest case, okay? All right, so now you try. A1 x to the first. That's the simplest case, right? How many multiplications? K equals 1. A1 x to the first. No multiplication, x to the first. That's just one multiplication. When k equals 1, your answer is 1. How about that? So you get the answer, not k plus 1, right? Yeah, because when k equals 1, you get k. Yeah. So here you can see our first strategy that's effective, right? Yeah, you test it. But when you test it, you use the simplest case to test it. Then you can get an answer. You see? Yeah. And that strategy we will use many, many times. You will see, very useful. Very useful. Okay? Yeah. All right. Yeah. Next question, is this algorithm efficient? Yeah, so here, all right. Are we satisfied with this solution? Yeah. At this point, it's hard to answer this question, right? Why? Because no comparison, right? We only have one solution. Nothing to compare. If you only have one solution, that means there is no better solution, right? If there is no better solution, you have no choice. That's the only solution you have. Even you complain, that's your only choice. But if you have two choices, that's different, right? One must be better than the other, right? Then you can say something. You can say, oh, this solution is not as good as the other one. So we should take the other one. Yeah. So that's the point. Yeah. So we do not know how bad it is. No comparison, so you don't know. Until we can do some comparison. Okay? Yeah. All right. Yeah. All right, so here we need to go one step further. We need to find the performance number. So what's the performance number? Performance number, another way to say efficiency. Right? Here we have efficiency concept, but it's very abstract. So what's the efficiency? Right? Very abstract. Yeah. Here, sometimes we call performance number, same thing. Right? Same thing, different way to call the same concept. Yeah. Yeah. Right? Yeah. All right. So here, let's continue the analysis. Yeah. Find the number of operations. Here we only have two operations, additions and multiplications. But we need to find those numbers, specific numbers. We don't want to talk about something vague. We want to talk about concrete things. Yeah. So we need to find those two numbers. Yeah. So the first number, here we Yeah, before we do that number counting. So here we do number counting. Before we do that, we need to make some assumption. We need to make some reasonable assumptions. Reasonable assumptions. Now, sometimes we need to do it. Yeah. Because here, look at one thing. One question. We have two operations, right? Addition and multiplication. How do you compare addition and multiplication, right? Apple and pear, right? How do you compare two different fruits? How do you compare, right? So we want to equalize. Because here we have to compare. We want to equalize two different things, all right? Here there are two things, addition, multiplication, but we want to equalize in a certain way, in a certain reasonable way. Yeah. Reasonable, then we can count them together. Count them together, okay? All right, so that's the assumption we need to make here, reasonable assumption. Yeah. All right. Okay, yeah. So here, when we make reasonable assumptions, we should not change our original problem significantly. Yeah. We should preserve our original problem, the typical property of our original problem. Otherwise, it's not fair. We are solving a completely different problem. We don't want to do that. We want to solve the same problem. Yeah. So we should be very careful when we make extra assumptions. Yeah. All right, so here, let us assume each addition takes 1 unit of time. That specific number is not important. 1 unit. How large is 1 unit? That specific number is not important. Yeah. Could be 2 nanoseconds. Could be 3 nanoseconds. You know nanoseconds, right here, because we use computer program. So we should use nanoseconds. Okay, yeah. The basic unit, nanoseconds. Okay, yeah. All right. So here, the unit, certain number of nanoseconds. You know the nanoseconds, how big it is, right? Nanoseconds? Yeah. Yeah. 1 nanosecond, 10 to the negative 9th power of second. 1 billionth of a second. Okay? 1 billionth of a second. That's the modern computer need for typical addition in that unit. Modern computer. Okay? Yeah. So we use that. Yeah. All right. Each multiplication takes 10 units. That's approximate assumption. 1 to 10 ratio. Yeah. So that's what I mean, reasonable assumption. It is pretty close to the real world ratio. Close, not exact. Yeah. Here it's not exact, but pretty close to the real world ratio. Okay? Yeah. But we don't need exact, right? Yeah, we don't need exact. So that should be good enough. Yeah. 1 to 10 ratio. Yeah. When you do one multiplication using the same amount of time, you can do 10 additions. That's approximately in that ratio. Okay, all right. Now, we can simplify, with that extra assumption, we can simplify the setting without changing the difficulty. Do we make the problem easier? No, still the same problem, but our discussion is easier, right? Yeah. The problem still, we need to solve the same problem. The discussion, now we need to compare apple and pear, right? Yeah. So we solve that problem. Okay? Yeah, we convert apple to pear, 1 to 10 ratio. Yeah. So we just count the number of units we need solving this problem. Okay? Yeah. Next, let's do the work. Yeah, let's do the work. All right. First, let's count the number of additions. In this case, number of additions. Can you tell me how many additions do we need? Yeah, good. Good, great. Oh, you're raising hand. So what's the number? Also n, good. It's the same. Anyone wants to say n plus 1? No, because there are n plus 1 terms, right? Is it n plus 1 terms? No, there are n plus 1 terms. Because you come from 0 through n plus 1 coefficients. Okay? Yeah. But the number of additions, it's n. One fewer than the number of coefficients. Okay? Yeah. Yeah. So, all right. Okay? Yeah. That's the first step. Answer is n. Counting technique. All right. So here, although you can answer give me the correct answer immediately, can you both tell me what kind of technique do you use? Or you use non-technique just by your intuition. So can you say something? One of you, say something, the method you use?
For how I determine how many additions there are?
Right.
Well, I just if you look at the polynomial, if you imagine that n is equal to 1, then you just add a0 to a1x, so that's only one addition. So then every time you add another term, it adds one more addition.
Good,
so it's
good,
less than.
good. You basically apply the similar strategy we use. One simplest case first, then generalize that idea, right? Yeah, yeah, that's effective strategy. You apply it another time. That's good. Can you say something of the method you use? Okay.
Pretty much the same exact thing.
Yeah. All right.
With a sub 0, obviously, as soon as the exponents get involved into the polynomial,
Yeah.
that's when each addition gets added on.
Good, good, good. All right. Yeah, yeah. So here, the reason I ask you that question, it looks like so simple. Why I ask that question, right? It's such a simple question. Why I spend time asking you that? Actually, it's not. So there is something. So here, I draw the underline counting technique. This counting related to some counting technique. Some technique is there. Some technique is there. Yeah. So what's that? Yeah. All right. So here, let me give you a little more information here. Here, dot, 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 you see many dots, right? Dot, dot, dot. Yeah, because we cannot list all of them, right? So that's why usually, we want to skip those terms. Yeah, we don't need to list all of them. Yeah, but we show the pattern, right? Yeah, although we skip those terms, but we can imagine the missing part, the pattern. We can view the pattern. So there is no problem we skip those terms. All right. But ask yourself, when you see a lot of da da da, do you feel something uncertain in your mind when you do the count? Because when you do the counting, you need to deal with the da da da. How can you deal with the da da da? Right? Think about that. Deal with the da da da. Okay? Yeah? Right? So, here. Yeah. Because for this situation, it is easy, but when the situation is not that obvious. So, yeah. Here, something let's look at. Yeah, let me just. Not changing. Yeah. All right. Yeah. Okay. Because when you need to process, deal with that da da da. Yeah. Look at this. Suppose I draw a polynomial a2x x squared plus a4 x to the fourth plus da da da. Okay? Yeah, I give you the pattern. I show you the pattern, right? Yeah. a2n to the x to the 2n. Yeah. Now if I ask you how many additions, can you get that? How many additions? Okay?
Still n.
Yeah, good, still n. Yeah. But do you feel it's harder than that one? So for every one of you, do you feel this one is a little harder than that one? All the same, you feel no problem, you feel fine. So you can figure out, okay? You can figure out easily, all right? Yeah, because here the issue is, so if I draw A1, A4, and so on, Here you can see when I change the subscripts, that could make the problem a little harder to figure out. Okay? Harder to figure out. Then when you do the counting, in order to count it in a right way, you need some counting technique to help you get it right. Okay? So here, this counting technique, I want to point it out. That's called counting by reference. Counting by reference. When you have a reference, it's easier to do the counting. If you don't have the reference, then it's hard. You need to imagine. You cannot catch it. You need to imagine it. So what is the reference? Here, let me point it out, the reference. All right. The first addition, here, look at this first addition. Can we associate it with something that's easier? We associate the first plus sign to another object, but that object is more obvious than that plus sign. That's the reference, this method. Can we associate the first plus sign to the subscript 1? Can we associate the second plus sign to a2 x squared, the subscript a2, and so on? So each plus sign we associate with some subscript, right? That kind of association is one-to-one correspondence, right? But when you count the number of plus sign, is it hard to keep track of it? It's relatively hard to keep track of it, right? Because all plus signs look the same. How do you keep track of it, right? Especially when you have dot, 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 how do you keep track of it? But now, when you look at the subscripts, 1, 2, 3, 4 through n, how to keep track of those subscripts? They are natural numbers, right? You don't need a special treatment to keep track of it, right? They're natural. 1 through n. Nothing is missing here. 1 through n. Okay? When you count the number of plus sign, that's the same as counting number of subscripts, right? And counting number of subscripts, that's obvious. 1 through n. Counting plus sign, you need to keep track of it. You need to, do some work, right? So here, that's the technique of counting by reference. Here, let's associate plus sign with 2, plus sign with 4. 2 times some number, okay? The plus sign, last one, 2n. 2 times n, okay? Now you count the number of plus sign, the same as counting number of subscript, 2, 4 through 2n. That's also n. So this method we call counting by reference. You only need to find appropriate reference. Then you just count different objects, subscripts. Okay? You do not count plus sign directly, but you count number of subscripts. That's much easier. We will have many situations like this. Many situations like this. So that's another method you can learn from this example. All right, so the essence of this method, you need to discover one-to-one correspondence. That's one-to-one correspondence, okay? Between two mathematical objects. The first mathematical object, plus sign. Second mathematical object, subscript. Okay? 2 objects. you establish one-to-one mapping between them. Yeah. Then, yeah, so here, let me erase this one. Yeah. Let me erase. Yeah. Now, object 1, object 2, one-to-one correspondence. But for object 1, relatively hard to count, plus sign. It's hard to keep track of it, so relatively hard to count. But object 2, easier to count. Yeah, 1 to 3, natural numbers, easier to count. Yeah, but we know they are the same. One-to-one correspondence, we just count the easier one. Okay, then we can use it for the harder one. Yeah, that's the technique. That's the technique. Yeah, yeah, it's useful. Yeah, in our everyday life. Yeah, this kind of reference method, it's useful. Okay, yeah. All right, yeah. Any question? Yeah. Simple but effective. So you can see for this class, we will learn a lot of things, pretty simple, but very effective. Yeah. So if you use them in the right way, yeah, whenever you have the right situation, if you use in the right way, you can get correct answer quickly. Yeah. So that's something we will do in this class. All right. Answer and units of time. Yeah. All right. Well, yeah. We finished the first topic. Now the second topic, estimate the cost. Yeah. We estimate the cost. Yeah. The cost, computing cost. Yeah. Computing cost in computing time, the time spent solving this problem, estimate the cost. Yeah. All right. Yeah, the same problem again, but we need to evaluate. We just count the number of additions. This time, we need to count number of multiplications. Okay, yeah, all right. Count the number for each term. Yeah. Actually, we did it before, right? Yeah. So we did it. Yeah. This time we need to add up the total number of multiplications. Yeah. Accumulate all the number of multiplications. Yeah. All right. Try simple. Yeah. Yeah. Simple example. Actually, we already passed this step, right? Yeah. Try simple. Yeah, but we passed this step. The answer is K. Yeah. Yeah. We go to the next step. The next step, here we do the chart. The first term, 1 multiplication. Second term, 2, 3, and so on. The last one, n. Yeah. Here we need a total here. Right? Is it easy to find a total? Sum of all the numbers. Do you know the formula? Everyone should know the formula. Simple. Yeah. Yeah. Yeah, yeah, right. This formula. Okay? Yeah. Yeah. So we get the total, this is the total number of multiplications. Okay. All right. Yeah. But we need to convert it to the units of time, right? Yeah. Yeah. In order to putting together addition time, multiplication time together, so we need to use the same unit. Yeah. So converting to the units in our assumption, extra assumption we made, so we multiply this number by 10. Each multiplication uses 10 units of time, 10. Yeah. So you get a 1/2 times 10, you get a 10, 5. Yeah, 5n times n plus 1. So this expression gives us the total units of time we need to compute, to find the value of the polynomial. Yeah. We have concrete number. This number. Yeah. So the next question, how to reduce this number. Yeah. Because this number, it looks pretty big, 5n squared plus 6n. Looks pretty big. So the next question, is it possible to reduce that number a little bit? We want to find the same answer, but we don't need that many units of time. We want to save some units here. Using some smart way. You have to use some smart way. Otherwise, how can you save? How can you save units significantly? Yeah. It has to be very smart methods.
Like if you know x squared, to calculate x cubed, you just need to take the old x squared value and multiply.
Good. Good. His idea is so good. Yeah. Get it? Yeah. I'm very happy to hear that. His suggestion, very good. What he says. All right. Look at here. 3 multiplications where we will calculate this one. What he said, when we calculate x cubed, we just use the value of x squared because we already have it. We just need one more multiplication, we can get x cubed. Why? We don't need to do 3 multiplications, right? We just do one more multiplication from x squared to x cubed, then another multiplication here, so we can reduce by 1. But this idea, if you apply it on all the other terms, you can save a lot, right? That's a great idea. That's a great idea. That's what I call creative. Now, if you can do it that way, yeah, so you deserve that credibility. Creative. Yeah. Yeah. So in this class, we encourage that kind of behavior. Creative. Yeah. All right. Improvement strategy. Okay. Yeah. Do some observation. Yeah. We need to explore some special property so we can take advantage to reduce the number of operations. Here, first, based on our assumption, the cost ratio for the multiplication over addition 10-to-1 ratio. Yeah. What does this number tell us? 10-to-1 ratio. That's pretty big number. As a ratio, it's a pretty big number, 10-to-1 ratio. From this big ratio number, what conclusion can we get? Reasonable conclusion. Yeah. Yeah. So let me point it out, the conclusion we get. Yeah. When you do the reduction on number of multiplications and a number of additions, where is your focus? When you do reduction, you should put more focus on multiplication reduction, right? Because the gain is big, right? Look at that. If you can reduce multiplication by 1, then the benefit you have, that's the same as you reduce 10 additions, right? Yeah. From the time you save 10, 1 multiplication equals 10 addition reduction. So then that means when you have limited investment to put in this algorithm improvement, you should put as a multiplication reduction, right? Because the gain is bigger. The gain is bigger. More cost-wise, better decision here. Yeah. All right. Focus more on multiplications because the gain is much bigger, 10 times bigger. Yeah. All right. Yeah. Strategy. Our strategy: reduce the number of multiplications. That's our main focus. Okay. All right. The question. Next question. Execution. Yeah. We have the strategy, but how do you reduce it? How do you do the reduction? How do you do the reduction, right? The execution part, not easy. Yeah. Okay? Strategy time. When something not easy, you need some strategy, right? Yeah. Think about it. So what strategy you like to use here? Strategy. Okay? We just learn. Use that strategy repeatedly. Try the simple case, right? Can you try simplest but non-trivial? If you try trivial, nothing you can get. Because it's trivial, you can get nothing, right? But simplest, but non-trivial. Non-trivial, okay? Implement that strategy. Yeah. Reduce number of multiplications. Yeah. Yeah. This number we want to, yeah, this is addition number. Yeah. It looks like it's hard to cut, hard to reduce. This number so big, we have a lot of room to do the reduction. Yeah. So we should put our investment here. Okay? Yeah. Investment here. Yeah. All right. Next, now, for the execution step. Yeah. All right. So we need to look at the details for this question. All right. All right. So now the strategy, simpler case. Yeah. Because here, before we have any experience, when we do some experiment, we want to start from simpler case. Yeah. So that strategy, you can see, that's the most frequently used strategy, right? Yeah. You know, most frequently strategy we use. Yeah. All right, let's do the work. When n equals 2, that's a simple but a non-trivial case, right? Yeah, simple, non-trivial. So we can get some useful information here. All right. So we get a quadratic polynomial, right? Quadratic polynomial. Yeah. So we want to try very hard to reduce the multiplications. All right, let's look at the property. When you look at these two terms, any special property you can observe, the property, the last two terms, any special property you can observe. Okay? Something. Yeah. Your observation is very important. Yeah. You can see in problem solving, our observation extremely important. Find something. Property. Yeah. Here, probably common factor. Can you see common factor x? There is a common factor between these two terms. That's the property. When you have a common factor, what usually do? What usually you do? Common factor. Factor it out, right? Yeah. Factor that common factor out. Yeah. So here, we change the form. Yeah. Change the form. The same formula, but in a different form. Yeah. So we transform the problem. We change the structure for a new outcome. Yeah. We do not want to change its value, but we can change its structure. Same value in different structure. How about that? Okay? Yeah. So here, let's do factorization. When we do factorization, we change its structure. Yeah. Factor this common factor out. So this one has different structure, right? Yeah. Yeah. So these two, same value, but different structures. Okay? Yeah. Then, when we work on two different structures, let's look at the outcome. If we have different outcome, okay, yeah. Count number of multiplications for the first structure. 3, because the first term we need 1 multiplication. The second term we need 2 multiplications. 1 plus 2, 3, right? Yeah. That's the first structure. 3 multiplications. Let's count the number of multiplication for the second structure. Okay. All right. Addition, we do not count. Okay. Addition, we do not count. We only count multiplications. Yeah. So no multiplication inside the parenthesis, the first term. There is 1 multiplication inside parenthesis, 1, only 1. Another one, parenthesis, x times parenthesis, the second one. So you can see adding these 2 numbers together, we have 2 multiplications. Can you see improvement? From 3 to 2. Reduction. 1 multiplication is reduced. 1 multiplication is reduced. How about that? 2 different structures, but the outcome will be different. See? See? Conclusion. The conclusion. Yeah. If you can explore factorization property, if you can do factorization, you can save number of multiplications. The reason we can save because we take advantage of factorization property. Factorization. How about that? Okay. So the factorization technique, yeah, we call it, it's a technique, factorization. Okay. Factorization technique can help us get the gain in time units, yeah, time, gain, multiplication reduction from 3 to 2. That's the conclusion. Yeah. For a simple example, you can already see significant gain. So this is significant, right? Yeah. 3 to 2. Although a small number, but significant. Okay? All right. The question, can we generalize this idea to the general N? General N. Okay? Yeah. Here, after we work a simple case, yeah, or simpler case, yeah, some simpler case. Now, we have the experience here. We have the conclusion here. Next, we want to extend it. Generalize this idea to general N. General N. Then it's reasonable we can expect better solution, right? So here with the knowledge or experience collected here, we expect some nice improvement when we work on the general case. Okay? Yeah. All right. Yeah. All right. Yeah. So because it near the, 3:30. Yeah. So because we still, when we work on this general case, a lot of discussion. Yeah. Still a lot of discussion. Yeah. So I will leave to the next time, our Wednesday lecture. Wednesday at the beginning. So we complete this first. Then we start new topic after that. Yeah. But one thing, yeah, just 2 minutes before we end, yeah. One thing is this example, our first project about this example. Our first programming project. Yeah. We will see a good algorithm, a bad algorithm, how much is the difference? Yeah. So I want to show the power of a good algorithm. When you do algorithm in an extremely smart way, how much gain you can get? How significant? Yeah. I let you feel about it. So that's our first project. You can feel about it. Okay? Using the first algorithm, the straightforward one, the plug-in one, okay? You sit there waiting 1 minute. 1 minute. Is that long? 1 minute. 1 minute response time. Feel about it. Is that long? You type enter, waiting for the output. You need 1 minute to get it. It looks like a century. 1 minute looks like a century, but that's the response time. But the second one, okay, see immediately. Fractional of time. Then you will see the huge difference. Okay, that's our first project. You see it, you will see it. So you will see the power. That's the power of algorithm. Okay, the power. All right, so that's it. Yeah. So that's our first lecture. All right, so oh, sorry. I muted. Wow. That still didn't tell me I'm mute. Sorry, but I will post the video. Yeah, I will post the video. Yeah.